Ladies and gentlemen, today I am going to present my work on enhancement of adsorption performance of NH3, that is ammonia gas molecule, towards cyclo carbon, and effect of substitution doping. This is the presentation made for the DAE-SSPS convention of 2021. Uh, this is the combined work of my colleagues and me, that is Darshil Narayan and myself, under the guidance of our guides, Dr. Q. Vyas, Professor Jha, and Professor Chakrabarti. So to introduce, ammonia is a colorless gas with the multiple hazards whose detection is highly demanded. Colorless carbon allotropes such as graphene, carbon nanotubes, etc. have been extensively used as the that is gas sensor, as we know. Uh, Cyclo carbon, or simply we can say C18. Okay, it is the most recent allotrope which can also be employed for the gas detection. In this work, we have investigated the absorption performance of NH3 gas molecule towards pristine and boron and nitrogen doped nanocluster. Well, in a computational methodology, we have used first principle derivation theory, that is ab-initio calculations, the omega b 9 sun xt hybrid functional and 631 plus GDP basis set. The package we have used is a Gaussian 09 and Gaussian for the uh, visualization purposes. Uh, the interaction between NH3 gas molecule and C18 nanocluster we can calculate by this formula. Let us discuss about the results. So first of all, the homolumo energy gap for pristine C18 is found to be 6.74 electron volts, which agrees with the reported data. For the interaction of NH3 with pristine C18, we have calculated the energy of absorption energy previously, which is found to be minus 0.23 electron volt. Obviously, it is a very we can see it indicates a very poor interaction. Therefore, we need doping for the enhancement of it. As a result of doping, so there are a total 18 atoms in the C18 nanocluster. So what happens that one atom of boron or nitrogen, it is being replaced by one of the carbon atoms. That means the doping fraction becomes approximately 5%. Okay, to be precise, 5.55%. Replaces one of the carbon atom, as I said. The optimization is done for 9 different positions. So that means there is a C18 nanocluster. So one position, let us say it is for a top, then one is a hollow, then one is under triple bond on the bridge. We can say one is on the either of the carbon atoms. So in a way, we are totally done 9 positions, and out of these 9 positions, the minimum energetic configurations are chosen because they are believed to be the most stable ones. So this first figure, okay, it has a consists of basically 4 figures, A, B, C, D. So it that is a C17N, that is a boron doped C17B, that is boron doped C18, and C17N, that is nitrogen doped C18. The structures before its adsorption and the structure after molecular adsorption. So in one of the cases, so as we can see the figure number A, we can see here that is a bond is formed, that is inherently the chemical structure is changing. So this would come in the chemisorption category, and if we use the in for C17N, so the interaction is happening uh, in the hollow of the C17N nanocluster. That means it would come under the physisorption category. So this one is chemisorption, this one is physisorption. These are the optimized geometries. As I said earlier, these are the minimum energetic configurations. Decrease in the homolome energy gap we can see in the figure number 2. That is, first we can see 6.74. After a boron dope, it comes to C17B for let us say 6.15. For C17N, it reduces further. That is C4.7 electron volts. So yes, we can clearly see a decrease after the doping. All right. Then so this is the table. That is first system. It is first on pristine C18, then second and 3 on C17N and C17B respectively. So as we can see, the energy is slightly increased. Negative sign shows that the process is exothermic. That means it releases the energy. That means 0.23, 0.25 and 1.81. So you can see there is a very good, or we can say very appreciable amount of value of adsorption energy we can see over here. The homolome energy gap, as we can see, it also increases, it also changes. That means first decrease by 5%, decrease by 0.42%, and 1.46% increase over here. Okay. Now we are not going for the increase, it's to be clear, but all right, and we will discuss about the recovery time later. Okay. So this table, okay, for C17N we can infer that the reduction of homolome energy gap in case of nitrogen doping. Okay. However, the value of its of energy is not quite appreciable, but for boron doped C18, or we can say C17B, the value of of energy are appreciable as compared to the C17N. We can say we can use C17B for the adsorption purposes, but the value of band gap is not decreasing. And why do we want decrease in band gap? Because at this table 1, all right, it also shows the values of change in homolome energy gap. So we know that is a homolome energy gap. Okay, it tends to change in the conductivity, just to leads to the change in the conductivity. So sigma conductivity is proportional to the t to the power 3 by 2 exponential Eg by 2 kt. That is where Eg is the homolome energy gap, sigma kt, sigma is electrical conductivity, Boltzmann constant is K, and T is the absolute temperature, as we all know. So if the energy gap decreases, that means our conductivity also decreases, and conductivity of when we do the sensing study experimentally. So the experimentalists use these terms, these parameters such as the conductivity and all that. So that's why we have included the conductivity term as well over here. Recovery time is another important property. We can define recovery time, as we know that is after the molecular interaction the adsorption happens. So this adsorb structure, okay, is about to, it will dissolve after some time, or it will so that it will the desorption will have so desorption will happen after some time. And so this is the formula for recovery time. Nu is the atom frequency. We can take nu as a photophonic frequency, K is a Boltzmann constant, and T is a adsorption temperature, as we saw earlier. The calculated recovery time, okay, of an acidic gas molecule is 7.3 nanosecond, 16.9 and 1.16 into 10 to the power 15 hours. So you can say that is for boron dope, that is C17B, the recovery time increases dramatically. So if the recovery time is so high, so that means We cannot use it as a sensor because for a sensor, recovery time needs to be in the order of microseconds, or if the our device is sensitive enough, then the nanoseconds. But if the recovery time is so high, then we cannot use it as a sensor, but we can use it as a molecule remover from the specific environments. So to conclude, in this work, we have studied the structural change, adsorption energy, and recovery time to understand the interaction mechanism between NH3 and pristine, or boron and nitrogen doped C18. After boron and nitrogen doping, energy gap (EG) reduces to 6.15 and 4.72 electron volt from the original 6.74 electron volts. Pristine and nitrogen doped C18 are not suitable for NH3 gas detection because of the physics of nature. Calculated absorption energy and a change in the electrical conductivity confirms that the strong interaction between NH3 and boron doped C18. Large recovery time suggests that we can use boron doped C18 as NH3 molecule remover from the specific environments. So here are my references. I would like to appreciate the show, that is the schema for developing high quality research. It is from Government of Gujarat, and Darshil would like to appreciate DST for the Inspire Fellowship. Thank you.